So can you guys see my screen?
Yes, sir.
So before we start, let me just like what are the main doubts and queries you guys have? Like, is there any specific thing you want me to stress upon? Like what? I will be just conducting. I'll do a brief recap of what sir has done. Then I will give some sample questions are there, so that we will solve. And yeah, so like that. So I will be conducting the recap. Okay, like you guys may already know that, but it could be useful. So if you have any doubt in between, you can stop me. Okay, just feel free to unmute and stop me, and uh, you can ask the question or query. And in case if at any time the voice is not audible or there's a network issue and all that, you guys let me know so that I can check. And also, this is a Zoom meeting, so I don't have Zoom Premium. So it is only a 40-minute meeting I have. So for 40 minutes, this session will continue, and then it will automatically get turned off. Then I will again restart it. Then you guys can again join. Okay, it's the same link. You don't need to worry about that. Okay, so all these sessions are getting recorded, and then I will merge them and I will upload on YouTube. Okay, so now I will share my screen. So good evening. I'm Calvin Joseph, and today I'm going to conduct a problem solving and doubt clearing session for week one. And this is for the course of digital controlling switched mode power converters and FPGA based prototyping. So, this is the NPTEL course which has been taught by Dr. Santanu Kapat of IIT Kharagpur. So, today, basically, this is the outline of the content which I'll be teaching and I'll be sharing from. So it consists of why digital control. Like I will be teaching why are we shifting, why there's a trend to go to digital control. And then further, what are the challenges in digital control? Like when we go for digital control, we will face some problems or some things which we need to overcome or some issues we might come. So that those challenges I will stress upon. Then some basic digital control architectures like what composes a digital circuit. We will just give a basic overview so you will get a basic understanding of what are the components of it. But it is not fully required for you guys. Then the digital control implementation platforms which are there. So in this course, it is more mainly the FPGA based prototyping. So the code, the Verilog codes are done in FPGA. And you guys uh, the codes are run for the various specific applications and various particular control techniques and modulation techniques. Those were done on FPGA prototyping codes are there. But there are other implementation platforms as well, which are used practically in the industry. So one is FPGA. The other one is microcontroller. Then there are also things known as ASIC. The application specific ICs also are there. So I will just be touching briefly on that. Then I will be focusing on the overview of feedback and feed forward control techniques which are there for these DC-DC converters. So these are important for because basically the course is built on these feedback feed forward control techniques. So it is very important for you to get a good basic foundational understanding of these control techniques. If you have any doubts, please ask me, don't hesitate. Then also we will talk about the various modulation techniques, how we are actually converting the control logic into required gate signals to actually run the DC-DC converter. So there are various modulation techniques are available. So we will be discussing about the various modulation techniques, and there's based on the particular requirement, a modulation technique would be pertinent for a certain application. So I'll just give you, the sort of overview of it, and based on whatever you want, which is useful for you, which works for you, that modulation technique you guys can use. Then also I will speak a little bit of the boost topology, boost DC-DC converter about the inductor current ripple, output voltage ripple, etc. That we will just basically touch upon. The boost DC-DC converters are one of the simple basic DC-DC converters. Okay. Next. Now, why are we starting with, why do we want to go to digital control? Like, digital control should have certain advantages or certain aspects which are not possible in analog control, or which would be quite difficult to do in analog control, and so we are shifting to digital control. So one aspect is its flexibility and programmability. Now, if you would do analog control, you guys would have studied in your BTech. You use an op-amp and some resistors and some capacitors to realize some PID controller or a type 2 compensator or something like that, or lag compensator, lead compensator, lag lead compensator. All of that, you find a transfer function. From the transfer function, you will find what are the RC passive components which you must connect to the op-amp, and then it will give you your controller, whatever you want. But there are certain limitations of that. One is suppose you want a resistance of 1.9 kilo, but in the market you might not get a resistance of 1.9 kilo. There might be 1 kilo, maybe 100 ohm. But 1.9 kilo ohm, exactly what you want, might not be available. Similarly, capacitances. You might want a capacitance of say 65 microfarad, but in the available market you might get 47 microfarad, 100 microfarad. So you might not get the value which you exactly want. Another aspect of these things, passive circuits, are they age over time. The values of these RC parameters might change. So it degrades over time. That is an issue. And if we want to update the PID gain, now I want to increase KP, then I have to change a resistor. So now I have to desolder the resistor, I have to again remove it, I have to again find a suitable resistor and connect it. So it is a long, tedious process. But in case of a PID control, if not PID control, any sort of digital controller code, I just have to change some variables, and I have to just dump that code into my application, into my platform, into my digital platform. I will just dump that code, which has the updated values of the gains for the controller, and it will run. Okay. And the another advantage is we can set some sort of time limits or some sort of non-linear limits, which we can set up, that we want the controller output to only range between say -1 to +1. But in analog control, doing that might be a bit difficult. Okay, so that way we can customize our code, and we can say we had written the code for PID control. Then we can change that code and we can make it for lag lead compensator. But it is the same platform we can use to implement the controller. We don't need to make any changes except changes in the code as per our requirement. Then we can also do fast and precise regulation. So it's very important for us, especially for the switch mode power supplies, that it should be stable power supply. So what are the disturbances which occur? That is, load variation. That is, some extra load current is drawn, load is added, load is removed from the circuit. So when that happens, what is the issue is that the load current changes. When the load current fluctuates, what will happen? The output voltage will dip or it will overshoot. There'll be changes in the output voltage. So for that, we need to regulate. As well as we cannot always guarantee that the input to our power supply is stable and fixed. There could be variations. So using digital control as well, we will try to.
Sir, could you please repeat the from start once? Just I have joined.
Okay. There is not much which I've taught. I just told about the outline, what I'll be teaching, as well as I've started with why are we doing digital control. Okay. You haven't missed much. Right? And also the recording also will be available later, so you can check that. So the link also will be put on the NPTEL website as well. So basically, I told about how using digital control we can update our controller, etc., without having the tedious process of actually soldering, desoldering, or removing components, finding exact values, etc. Another thing, okay, so fast and precise regulation, we need load regulation, good load regulation, as good input voltage disturbance also should be able to reject. Then communication interfaces. Now, using this SPI, serial peripheral interface, and I2C, these communication protocols are there. We can use this for communicating data from our converter to some main control unit, etc. So these things will enable us to, to have real-time monitoring of what actually is going on, whether there's any fault, whether there is any controller is working, etc. All these using communication interfaces, we can communicate data. Then fault prediction and monitoring. So it is very important that our product, that they should not be affected. Whenever there's a fault occurs, it should be able to protect it against it. So when suppose there's an overcurrent has happened, then it must disable the inputs. Suppose there's an over voltage, what it should do. If the temperature is rising, then what it should do. As well as suppose there's a dip in the input voltage, then what it must do. So, because when such anomalous situations happen, it would harm the application. And so what would be the suitable thing to do in that situation? Using digital control, we can detect that event, and then we can program it by saying that if the current level is above 3 ampere for more than 1 second, then you turn it off. And if the current level is above 5 ampere for more than 1 microsecond or some value, then you must immediately turn it off because it was a short circuit. But if it was overloaded, then it can wait for some time, it can delay for some time, and then it can actuate the protection. So all these flexibility we have in digital control. Another thing is efficiency and power saving. So
Sir, what is the need of communication, sir?
communication, like we want to know what is happening, what is the voltage level, what is the current level. So one example, let me give you. Now we have a specific application and it is not running, like suppose there's a light bulb. Okay, you just consider there's a light bulb at some place. It should not be operating because there's a person is not there. So if we can communicate such sort of data, then we will know what has to be on, what has not, what doesn't is not required to be on. Like suppose there's load management, other such facilities are there. So using these communication, we can we can communicate what has to be done. So there'll be a master who will decide, who will understand it, what are the specific requirements, what is the need of the hour. And based on that, it can give command signals to certain slaves, and they will be operated or controlled by the master as per the master what it feels is necessary. Such things are there. Those are a bit of an advanced thing. In this course, we are not going to be using such advanced SPI I2C. We will just be talking for a basic thing. But it's good for you to know that such things are there available. Such communication protocols are available and they are used, very highly used. So also there's one application of like the battery, how much it is charged. There's a battery management system. So for that to communicate the data of the battery's health, how much is the charge available in the battery, that it has to be communicated, the data has to be communicated to the management system. Then a management system will decide, okay, now I have put how much of charge I need to charge the battery with, or like is the battery getting heated up, or such things. So all these things require certain communication. So that's why SPI and I2C are there. Then efficiency. Like many times, if you see a digital watch or if you even see a mobile, it is inactive. Okay, it is not working at its maximum capability. It is working in a like in a snooze mode, or like it is a nap mode. It is not at its full capability. So what would happen if even if in this snooze or the nap mode or sleep mode, it is going with the maximum power it is monitoring, then what will happen? The battery will drain, power will be lost. So, but in case we know that it is not fully in functional use, my mobile, I'm not using the mobile, it can just operate with some low power, then what will happen? My battery's life will be preserved. And then when I get some sort of notification or when I start using it, I need to increase the power output of whatever my converter such that it can perform the function. So for that, we can have power saving. So at a light load, when it is not required to be used, it can work in a dim power. But when it has to be used, like when I'm watching a movie at maximum brightness, then it will require more power. So based on the requirement, it will dynamically change how much power is going to be used. So that is something which can be done using digital control. And then another factor is compact integrated solutions. Now, in analog control, you have a resistor, capacitor, they're very bulky and it takes a lot of space. So, but you see all your mobiles, they're so small. You see the digital watches, they're all so small, they're so compact. So how has that been possible? Because there have been advances in electronics and also they've made something known as IC, integrated circuit, where quite a bit of the functionality is in one chip. Okay, so there's a PMIC. PMIC stands for Power Management IC, where the switches, all the main control logic, etc., is in that IC. While the passives, like the inductor or capacitor, the filter components are on the external side. So those are some power management IC. Next is digital ICs are there. Also, there's a microcontrollers also are there. So these integrated solutions, these integrated chips, they can be used for controlling many things. Okay, and they are very small in size. That is helps digital control to achieve higher power density solutions. Next, but whenever we are going for digital control, we will also face certain challenges. It is not like you will get all the benefits but no problems. There are certain challenges like ADC resolution. ADC resolution is how small the voltage level the ADC can sense. Also, there is a quantization error in the ADC. So when there are very small signals, very millivolt range, etc., they might not be sensed by the ADC properly. So what to do in such a situation? Also for low duty ratio operation for these buck converters or boost converters, there could be certain issues. Then whenever see what happens with the ADC, ADC stands for analog to digital converter. There's a signal is at the input of the ADC. That is an analog signal that has to be converted into a digital signal. So it doesn't happen in a second. It doesn't happen quickly or automatically or instantaneously. It takes some time. So the ADC first has to sample the signal. Okay, once it samples the signal, it has to convert it into a digital signal and give the digital output. For doing that, there's a delay, and that delay can hamper the stability of our system. So that also we must take into account. Another thing is power consumption. Although they consume less power, but if we increase the switching frequency or the sampling frequency for the ADC, then it has to operate continuously. If it is operating like that, then obviously it will draw more power. So there's some trade-off between how fast we want to sample the signal and how much power we can dissipate. Another thing is the bit size of the ADC or the DAC or whatever. If it is a 4-bit ADC, assume it is a 4-bit ADC, then it will have some certain resolution. But if it is a 12-bit ADC, then the resolution will be even finer. Then even finer, small changes in the signal, it can detect and it can sense. And that is important. But we cannot indefinitely increase the size of the ADC, bit size of the ADC. So those are some sort of trade-off challenges which the designer has to consider and take into account. Another thing is noise and sensitivity. So these are digital signals and they could be coupling between the signals. So whenever they are designing the board for these digital circuits, they have some specific guidelines which they have to take into account. The proper grounding is required, shielding between the signals, all that has to be taken into account. Then we can implement complex algorithms in digital control, but we must also make sure that our platform is able to has a capability and the processing power to implement that algorithm. Okay, so those things we must take into account. And if it is running implementing a very heavy algorithm, then it might get heated up. So then if it is getting heated up, then what we must have a coolant. All those things have to be taken into account. So in this thing, we will be focusing a lot on these buck boost converters and specifically the buck converter. And this is the this is a buck converter, the schematic of buck converter, and this is this how we implement show it in a circuit level. But in the practical circuit, it is of this form. Here's the buck converter PCB printed circuit board available over here. So I will describe what and all is there in the next slide. Then we have a signal conditioning board. So the buck converter is connected to the signal conditioning board via these connectors. Okay, these connectors are there, as well as the ADC, etc., are present in the signal conditioning board. So the signal from this board is taken over here, and the ADC will convert that analog signal into a digital signal, and that will go to this FPGA. Okay, this is the FPGA. This is the digital platform in which we have burnt our digital code, which will be implemented. So this signal conditioning board is mounted on top of this Xilinx FPGA kit. Okay, this signal conditioning board is mounted on top of the Xilinx FPGA kit. So it is not shown over here, but at the bottom side of the signal conditioning board, there are male headers, okay, male header pins. So those male header pins go into these female sockets, okay, female GPIO headers of this Xilinx FPGA kit. So this signal conditioning board is mounted on the Xilinx FPGA kit, and the signals of this signal conditioning board are transferred to the FPGA from here. So this actually is my field programming gate array, FPGA IC, and these are the pins of this IC. These pins are connected to these points, okay? At these points, these are the GPIO headers. So I will put my signal at the GPIO header, and it will be transferred to this IC from here, okay? I will explain this in more detail. We'll proceed to the next slide. So this is the hardware prototype. Okay, this is the enlarged version. So this is the buck converter or boost converter board. It can work as a buck converter or boost converter based on certain configuration changes which can be done. How? So it is now configured in buck mode. So what is a buck converter? It steps down the higher voltage to a lower voltage. So this is the high voltage side and this is the low voltage side. So this is the input and this is the output. Then they must have a common ground. So this is the ground terminal. Okay, so I will apply the input over here with respect to this ground, and the output I'll measure over here with respect to this ground. So it's the same ground. Okay. Then in a buck converter, if you see, there are two switches, S1, S bar. Okay. This is the main switch and this is the complementary switch. There's an inductor, there's a capacitor, and there's a load resistor. There will also be input side filter capacitor also is present, but it is not shown in this schematic diagram. But in the practical hardware, it is there. So here, this is the input side, and these are the input side capacitors. This is the output, and these are the output side capacitors. Okay, this is the inductor of the converter, and we have kept a wire. If you see, this wire is over here. This wire has been specifically put so that we can connect.
Sir, why the capacitors are needed at the input and the output?
Okay. There's for the output side of a buck converter, the LC acts as a filter. Okay, it will filter out the harmonics to result in a stable DC output. Okay, with some small ripple in the voltage. At the input side also, there could be variations of the input voltage that we do not want. So to minimize those variations, we connect capacitors. Okay, so the capacitor's basic function is to stabilize the voltage. Okay, so this is at the input side and the output side. So now this wire is placed, and a current, when we are actually running this board, there will be a current probe which will be put around this wire, and it will sense the current flowing, and that it will display on the oscilloscope. those are very high bandwidth current probes and very costly equipment. Those are there. Then this U1 and U2 are the MOSFETs. Okay, U1 and U2 are the MOSFETs. Then this MOSFET is this U1 and U2. Okay, and these are the load resistors are placed. And then there are certain sensing components for the stuff. So these signals go from this power board to this signal conditioning board. They're connected via this header. And then there is a DAC and an ADC present. Okay. And these are, certain user push buttons. Okay. If I connect it, what they do with these push buttons is they program certain stuff. Like if I push the button from here to here, then it would result in some sort of, it could cause a load transient. It would cause the converter to go from open loop operation to closed loop operation. All this functionality you can program by these user push buttons. Okay. And then these are the stands on which the board is placed. So now we will go to the implementation, CMOS implementation of a 2-input AND gate. So if we know the logic for the AND gate is Y equal to AB. Okay. So this is for AND gate. If we do 2 times NOT, it will still produce the same output. So we are doing NOT of this plus another NOT. That's why the bar is placed. And we know AB, AND of AB, the NOT of that will be A bar plus B bar. Okay. Which is equal to X bar. So X is the complement of Y. This meeting will end in 10 minutes. So after that, I will again start the same meeting with the same link. So you can again join after that. Just a general reminder to you guys. So this is a NAND gate. This is A, this is B. Similarly, A and B is connected over here. And this is X. Now what we will try to understand is, this is a NAND gate. NAND gate's truth table is like this. It is A, B, and this is X. So this is 0, 0. This will give 1. 0, 1. It should give 0. 1, 0. It should give 0. 1, 1. It should give 0. So only when both the inputs are 0, it should give 1. Okay. And in any other condition, it should give output as 0. So A and B are there. So this is a PMOS circuit. This is a PMOS transistor, and this is a NMOS transistor. All right. So when I give an input 1 over here, this is off, and this also will be off. Whereas this will be on, and this will be on. So when you give an input of 1, 1, the output will be 0. But if you give an input of 0, the output will come out to be 1. Now we will go to an AND gate. So we have seen that this is inverting the logic. Okay. So now after this NAND gate, this is same. This is the same NAND gate. Now I will take the output of this NAND gate to a NOT gate. Okay. So this is a NOT gate. So for the NOT gate, what it is, if you give an input, if this is 1, okay, assume the signal which comes here is 1. When the signal is 1 here, means it is high. So what happens is this NMOS transistor turns on. When this NMOS transistor turns on, the output Y will be equal to 0. Okay. Now, instead of 1, I apply 0 comes here. Okay, if it is 0, then what happens is this does not turn on, but this will turn on. Okay, so when this turns on, the output over here goes to VDD. VDD means it is actually 1. Okay, so this is how from this is a NAND gate, and then we apply a NOT gate, and then we get an effective AND gate. Okay, and this is the number of transistors which we require here are 6. Okay, so 1, 2, 3, 4, 5, 6 transistors are required for this implementation. So this stands, so this example is given like for understanding how if we want a particular operation, particular logical function to occur, then we have to design the circuit with various transistors and we can get the circuit with the minimum number of transistors. Now, we will consider lookup table based implementation of some logic. So these are certain cells which are actually known as SRAM cells. They have 4 cells, okay? And these are known as, these are the digital muxes. So if you see, these are the digital muxes and these are the select lines. So A and B, they are the input. They're based on the select lines, it will select particular thing, particular output, and Y will come out with that. So if A is 0, if A I put as 0, okay, let me start from B. So this is B. Now assume I put B as equal to 0. If B is 0, the output of this digital mux, see a mux is, there's many inputs, but it has a single output. And the output is selected based on a select line. So when B equal to 0, so it will select the output to be Y2. Okay, it will select the output to be Y2. This same select line is going to this mux as well. B is 0. So it will select the Y0 to be the output. There are 2 inputs to this digital mux, but it will select Y0 because of the select line. So to this digital mux, there are 2 inputs. One is Y0, another is Y2. Now, if I put A to be equal to 1, A is 1, then the output of this will be equal to Y2. But if A is 0, then this output will be Y0. So in this manner, we can select what data we want based on the value which we assign to the select lines. So we have 4 data bits, 4 bits, and based on the select lines, we can get whatever bit we want, whatever is with value which is stored in that particular cell. So this is the truth table. Based on whatever inputs of A and B I'm giving, I'm getting the output Y. So if we want to implement an AND gate based on this implementation, what we have to do is Y0 in this situation should be 0. Y1 also should be 0. Y2 also should be 0 and Y3 should be 1. So if we store Y0 to be 0, Y1 we store to be 0, Y2 to be stored to be 0, Y3 is equal to 1, then we will get, when we select AB according to this, we will get this output. But now I don't want an AND gate. I want to implement an OR gate. So we know for an OR gate, the output will be 0, 1, 1, 1. So what I have to do, so now I don't need to change the setup. The only change which I need to do is at Y0, I will store 0. At Y1, I will store 1. At Y2, I will store 1. And at Y3, I will store 1. So if I set those as the bits in those SRAM cells, then I can implement an OR gate using the same hardware. I don't need to change the hardware. I just need to change the values just stored in these SRAM cells, and then I can implement another logical function, which was not possible in the previous diagram of an AND gate. I have designed it using the CMOS transistors, and I've designed it to implement an AND gate logical function, but it cannot implement any other function. But in this case, I can implement the function I want, the desired function I want, using the same hardware. Only changes I have to do is I have to reprogram these values of Y0, Y1, Y2, and Y3. So that is the advantage of this. This is a lookup table based implementation. LUT stands for lookup table. Okay. So how many functions I can implement? So Y0, Y1, Y2, Y3. Y0 can either be 0 or 1. Y1 also can either be 0 or 1. Y2 can also be 0 or 1. Y3 also can be 0 or 1. These are the possibilities. So the total number of functions which I can implement, possible function which I could implement is 2 raised to 4. That is equal to 2 raised to 2 raised to 2. So because there are n, your number of inputs are 2. So the possible number of functions I can implement is 2 raised to 2 raised to n. Suppose the number of inputs I change to 3, then the possible number of functions I can implement will be equal to 2 raised to 2 raised to 3. Right? So that way I can exponentially increase the number, what sort of function I want to implement, possible function I could implement. Okay. So now this is very attractive solution for me because same hardware, I just have to make some changes, just have to reprogram certain stuff, and then I can implement the desired function I want. But it has also some sort of something which is disadvantages, and we'll look into that. First, we'll look into CMOS implementation of the SRAM cell. So this is the SRAM cell, Y0, Y1, Y2, Y3. All these are SRAM cells. Okay, so the meeting will end in 1 minute. I will again start the meeting soon. So this is implemented using this setup. Okay, there's a NMOS transistor here, one more NMOS transistor here, and two and one NOT gate over here, and another NOT gate over here. So the total number of transistors required for this SRAM cell are 6. I require 6 transistors for this SRAM cell. So to store 1 bit of data, I require 6 transistors. 6. Now for this, because there are 4 SRAM cells, I require 24 transistors. 24 transistors I require to implement this logic. Now so this is for the SRAM cell where I'm storing the data, the bit which I want. Now I want to implement. So you guys are able to see the screen and hear that?
Yes.
Okay. So now we will consider this is a circuit for this is a block diagram for digital mux. So this is the select line, A and B are the inputs, and Y is the output. All right. This is implemented in this fashion. So if you will see, this is A is the input, B is the input, Y is the output, and S is the select line which decides which input it comes at the output. Okay. So now we will look into it. This is complete thing is known as a transmission gate. Okay. One transmission gate is here, another transmission gate is over here. The transmission gate, if you look, consists of parallel PMOS and NMOS transistors. So suppose I give S to be equal to 1. Okay. By this block diagram, I understand if S is 1, then Y will be equal to B. But now I will look into the circuit. How is this being implemented? I give S to be 1. That means for this NMOS will be on. Okay. And S is 1. It goes to the NOT gate. It comes 0. And for PMOS, if you give input 0, this PMOS will turn on. So both of these are on. So this input B comes at the output Y. Okay. So this is one transmission gate is there. And when S is 1, for this transmission gate, this is 0. So the NMOS, it is 0. So this will be off. For this PMOS, it is 1. So this will also be off. So this in A will not appear at the output Y, but instead input B will appear at the output of Y. So in this manner, the CMOS circuit is being implemented. So if we will see the number of transistors which are required to implement this MUX, which has 2 inputs and 1 output, will be 10. 1, 2, 3, 4, no, 6. 6 transistors are required to implement this. Okay, 1, 2, and in the NOT gate is implemented by 2 transistors as I showed previously. So 6 transistors are required. Now we will go. So what has happened in the AND gate, which we have specifically designed, the CMOS circuit, to implement only the AND function, the number of transistors are required, only 6 transistors are required. So, that's just very good. Like we don't want to have a large number of transistors. But if I want to implement an AND gate using the lookup table approach, these are the number of transistors are required. So there are 4 SRAM cells. 4 SRAM cells translates into 6 into 4. That is 24 transistors are required. Now I require 2 input side mux. Okay. So if we see over here, okay, this mux, first let us see, this mux requires 6 transistors. Okay, it requires 6 transistors. Similarly, then we would think that this mux also requires 6, this mux also requires 6 transistors. But if you would have observed, there's a common NOT gate is there. Okay, there's a NOT gate. In there's this NOT gate. Okay, that NOT gate can be common for this mux as well as this mux. So the number of transistors required for this is 4 plus 4 plus 2. That is 10 transistors are required for this section of 2 digital muxes. So anyone has any doubt in this? So this might be a bit confusing.
Sir, please can you explain CMOS implementation of 2-input digital mux once again?
Okay. This one. Okay. So this consists digital mux, 2 input digital mux. There are 2 inputs A, B, and this is select line S. This is the output Y. So the input goes to the output via transmission gates, and the transmission, this is transmission gate 1, this is transmission gate 2. Okay, and that is controlled by this select line S. Okay, this select line S controls which transmission gate is on. Now I assume I put select line, I give it to logic 1. If I give select line logic 1, then this NMOS of the transmission gate is high. Okay, this 1, so this is turned on. And this S goes through this NOT gate, and value over here is 0. Okay, value over here is 0. So what happens is this PMOS transistor also will turn on. So effectively this transmission gate is on, and at the output Y, I will get B. Also, what happens for this transmission gate is S is 1. So 1 goes to the PMOS, and if 1 is the input to PMOS, the PMOS does not turn on. So it is open. So A does not come over here. Similarly, for this NMOS transistor, since S is 1, it passes to the NOT gate and comes out to be 0. So this is still off. So this also will be off. So this transmission gate is off. So in this manner, using this transmission gates as well as this NOT gate, we implement a digital mux. Okay. So transmission gate requires 2 transistors, the NOT gate requires 2 transistors, another transmission gate requires 2 transistors. So in total, I require for one digital mux, I require 6 transistors. Okay, but in this situation, whether 2
one small. Can you please go to that?
Yes. Yeah.
If B is logic 1 and if B is logic 0, if B is logic 1 means through which transistor it will go, and if B is logic 0, then through which transistor it will close.
Okay. See, B can be 0, it could either, or it could be 1. That's what you're saying, right?
Yes.
Okay, so B is connected to this transmission gate over here. The input B is connected to this transmission gate.
Yes.
So we'll work with the assumption that S is 1. Okay, S is 1.
Yes.
So S is 1, this transmission gate is turned on, is on. So it is like a closed switch. That means the input will appear at the output. So whatever the input, it could be 1 or it could be 0, that same input will appear over here.
But there are 2 transistors in parallel, right? So through which one?
Yes, okay.
Through which transistor it will close? So there are 2 transistors, right?
Okay. Yes.
In B.
Yes. Okay. So it says like these transistors are acting as a switch. Switch can be either on or off. It can either be open or closed. So if S is 1, that means this is a closed switch. This also is a closed switch. So whatever is over here comes over here. It flows through both. It comes through both these transistors.
It comes through both.
Yeah, both.
In that case, only one transistor is sufficient, right? Then why do we need two?
Yeah, you could think like that, but this is for this electronics VLSI people, and there would be some practical requirements why they need it. Maybe the speed to turn it on, or the symmetry to turn on and off, and certain sizing of the transistor. Certain conditions could be there, so it is a requirement for them to have these things. I don't work in this field, so I don't know the exact solution for this, but I think it's a very highly advanced topic. But it is a requirement. That's why it is the
Oh.
standard way.
Okay.
Okay. So I will proceed further. Okay, so we have proved for the two input side mux, I require 12 minus 2. That is 10 transistors. And for the two input side mux, I require 6 transistors. So in total, I require 40 transistors to implement an AND gate using a lookup table. But if I use a specific set of designed hardware for CMOS transistors, then I can implement an AND gate with only 6 transistors. So ASIC stands for Application Specific IC. That is, I have designed the hardware for that particular application alone, and it would implement only that function. So if I do that, then I will get a designed hardware with a low number of transistors required. But if I want a certain hardware which can implement various functions based on my own specific requirements, my own terms and conditions, then the number of transistors which are required will increase, and that is 40 transistors. Okay. So this lookup table is what actually is a field programmable gate array. It is basically a lookup table. Okay. These logic blocks are actual lookup. Okay.
Sir, what exactly lookup table means, sir?
Okay. Let me go. Okay. So you are able to see this, right?
Yes, sir, able to see.
Okay. So lookup table is based on the input, it will select some particular function value output. Okay. That is, it is looking up at the input and it is selecting the particular output. So if the inputs are 0, 0, it will give this output y0. If the inputs are 0, 1, it will give the output y1. The inputs are 1, 0, it will give output y2, and so on. So it is like there is already a table which has already been defined in the digital platform. If these are the inputs, then it must give this output that is already defined. So it is looking up. The inputs are given, then to look up in the table that these are the inputs which I have, and then based on that it will fetch the output y0. So that is why it is called a lookup table. Okay.
So in that case, there will be 16 tables, you mean, already written for this in the memory.
No. That's the thing. There are not 16 tables. There's only one table. In this thing, there's only one table. But what I can change is I can change these bits y0, y1, y2, y3. I can change it according to my own terms and conditions. So in case this was 0, 0, 0, 1. Y0 is 0, y1 is 0, y2 is 0, y3 is 1. Then it will implement an AND gate. But in case this was 0, 1, 1, then it will implement an OR gate. So just there is only one table. Okay, at a particular instant, it is programmed for only one table. But based on if I want to change the function, then I have to reprogram the bits. I have to change the bits. So using a single table, I can modify it for another function. So it's like basically I can modify the table. It's not that I have multiple tables. I can just modify the table.
Okay.
So, sir, basically, you are saying 16 different combinations can be implemented using
Yes,
this.
yes. See, it could also just be
That combination is called.
sorry, you're saying?
Yeah, that combination is what you meant by function.
Yeah. Yes, because those combinations will determines the function output, right? So there are 16 possible combinations, like 16 possible, permutation combinations, etc. So there are 16 possible outcomes which can happen, 16 possible different tables which I can make, and that I can program one particular table at one instant. But if I want to change the table, I can change it. That is the advantage of this hardware setup. Well, proceed.
Sir, actually, we are implementing these MOS transistor circuits from the Boolean equation.
Yeah.
Sir, is there any way to know how to draw those CMOS circuits from the Boolean equation?
That will be under different course actually. So, you see, this
No, okay.
it is
Here
not.
we are just for just for the sake of understanding, we are
Yes,
using
yes.
here.
To just give you the brief idea of what exactly is a FPGA. Okay. So now my FPGA consists of like there's a multiple lookup tables. Okay. I told there's only one lookup table. Okay. For that particular hardware, there's only one lookup table. But in the FPGA, there like that multiple lookup tables are there. Okay. Because we just cannot have these two inputs. We have multiple inputs, multiple outputs are required. So we have this logic blocks. Okay. If I could just turn on that. Okay, so all these are like sort of different lookup tables are there. Okay. And I can interconnect this, programmable interconnects. I can connect one lookup table output as the input to another lookup table and so on and so forth. I can do. So there are various lookup tables are there, which I can program according to my requirements. There are programmable interconnects, which connects one lookup table to another and so on and so forth. There are input output blocks where I can read the data. Either I can send, if it is input, means I will send some data over there. I put 1 or 0, something like that. The output block, I can read 1 or read 0, such that. There's a RAM, this is there, the digital signal processing units are there. So it is a digital platform through which we can program what function we desire. Right. So the FPGA, field programmable gate array, consists of number of logic gates, large number of logic gates, which we can program it based on our specific requirement, and it will implement that function. So that is the advantage of FPGA. So we do not need to make again design that, like as you said, if I want to have an OR gate, how will I decide the CMOS transistors, all that you said, right? Someone asked that question. So that we don't need to do if we have a field programmable gate array. We just tell we want to implement this function, it will automatically connect as per the requirements to execute that function, to be able to execute that function. So we will not be just implementing an AND gate or gate in practical real life. It is a complex function which is made of multiple AND gates, multiple OR gates connected in various fashions, etc. So we cannot go basically into designing that in specific detail. Hence, we use the FPGA to translate our logic into a certain hardware setup, which can be used to implement our logic, but implement the logic. So that way we can change the logic which we want using the same hardware. We don't need to change the hardware. We do not need to again bring a new set of transistors, design it all over again and do. All right. Okay, then, so that's what it consists of multiple lookup tables and various, and flip-flop also can be there for connecting the output as desired. As per requirement, this is a mux which can select which output we want. So this is like a logic block of an FPGA. This is a logic block of this FPGA. Now, the FPGA used for this is the Xilinx Spartan 6. Okay, this is the Xilinx Spartan 6. This is the FPGA. Okay, it looks so cool and all. Yeah. So this is the FPGA kit which is being used. and these are the GPIO headers. Okay, so this is FPGA. It will have like around 80 pins or some amount of pins. All these pins are connected to these headers. Okay, these are connected to these headers like this. That is done in the printed circuit board. It is designed very well, and it is shown by Lab, etc. So all these pins are connected over here to these headers and to these specific, these are the LEDs are there. Okay, the LEDs are there. These are push buttons are there. All that crystals for the stuff are there. This is from where we get the USB input for the power, etc. What what is this? So over here we can connect our input, or if it is programmed to work as output, we can detect our output like that. Then these LEDs are there for, like, we can program that if suppose there was a fault has occurred, then the LED must be high, it must be on. If this fault has occurred, if one fault has occurred, this LED should be on. If over voltage has occurred, then this LED should be on. So that way I will know what fault has occurred. That can be done. Then these are certain switches are there. So if I press this switch, then the mode of operation should change from this mode to another mode. So all that I can program it. Okay. So that is why this is a sort of kit. This is a sort of kit. And we can implement our logic algorithms. We can reconfigure it. We can update it. We can modify it, etc. using the same particular kit. We do not need to change and redesign a new board and what. So that is the advantage of this FPGA kit. Okay. So this has been used in this course. The demonstration lectures and videos, this FPGA kit has been used. This Xilinx Spartan 6. Then this is STM32 microcontroller. Now, the FPGA has certain things, like it doesn't have the ADC or the DAC. Those are external to the FPGA. FPGA has advantages, but it doesn't have those peripherals inbuilt inside it. So it has to be interfaced to the ADC or to the DAC to run to get the data or to output data or etc. A microcontroller, on the other hand, it has ADC, DAC, many other peripherals inbuilt into the microcontroller. And like this is the STM32 microcontroller Nucleo G474RE board is over here. And these are, these headers. Okay, we saw it in the Spartan 6 FPGA kit also headers, and these headers also over here. And as over here, these pins also are connected as per our requirement to these headers. And these, these are known as the female headers, or these are the Arduino connectors. So, Arduino is a very popular microcontroller, which is student friendly, easy, and used by many electronic enthusiasts, etc. So if they want to use this STM32 microcontroller and interface that also an Arduino board, then they can connect it to these connectors, or you can also use it for your application. And then these are male headers. Okay, so you can connect signals over here. So if I assume, like, let us say this pin, okay, like this pin, I will program it to work as an input. Okay, so I will program it to work as an input. So I will give an input signal over here, analog input signal. Let us assume it's analog input signal. That will go to the ADC of the microcontroller. And the microcontroller will sample it and it will convert into digital data. So that is a microcontroller that has various advantages. And these are some push buttons also. Like push buttons are present over here also. This is a reset button which will reset it back to default. Like a restart button in our PC, like that, there's a reset button in this microcontroller kit. Also, there's this IC which is used to dump the code over here. And over here, we connect the USB connector. We will connect it to our laptop. So what is there in the laptop is my software, which I write the code. And using this USB cable, I will dump the code into this microcontroller via this IC. So all this are there. Okay. And the various other stuff, we can check it. Yes. Yeah.
Sir,
Yes.
actually, we saw in our initial slides, we saw there will be a power board, and then there will be a sensing circuit, and
Yes,
from that sensing circuit will be feeding the FPGA, and FPGA will be controlling the switch.
Yes.
Sir, where this in this loop where this board will come, sir?
This
This
microcontroller.
microcontroller board.
Okay, we have not.
Yes.
Yes. See, this microcontroller board has not been used for demonstrating the codes. It has not been run. Okay. But in case we want to use this microcontroller board, then those signals, okay, those particular signal will, let me just do the pen. So I like the sensed output voltage, assume this is the sensed output voltage, okay? This signal I will connect it to this pin. Okay, then the Q, that is the output of the logic. This is the gate signal. Okay, it will be coming from an internal timer. So that will come out from here. Okay, so this is going in, this is going out. Like that, I can use this board for running the logic. Is this what
So
doubt you have?
instead of FPGA, this can be.
Yes, instead of FPGA. This is an alternative for FPGA. And this also has some advantages, that also has different advantages. But in this course, we are stressing on the FPGA alone has been used for implementing the logic. But the same logic can be implemented also via a microcontroller, and microcontrollers are also used heavily in the industry. So see, you cannot use an FPGA for an application because it is very bulky, huge. But you see, this microcontroller is very small. Okay, such things are there. And that FPGA, if you look at this does not have the ADC, DAC inbuilt inside. Okay. So you have one more ADC, one more DAC, something else outside. But in this, they're all inbuilt over here. So it is most compact and a better solution. So in many practical chargers, etc. Yes.
Sir, in our FPGA can't be implement ATD, A2D or DDA using our code in the FPGA itself?
No, see, the ADC is analog to digital converter. So it is an analog signal. The FPGA can only handle digital signals. It cannot handle an analog signal. So what happens is when we are running it, the ADC, we have an external ADC. Let me go. Okay. So I have a signal. Some signal will come from here, it will come here, and it will go to this is the ADC. Okay, this is my ADC. Okay. So in this ADC, the signal will come and it will convert that into some digital data. So that signal will be converted to digital data, and that digital data will go to the FPGA. Okay, listen, this is the signal conditioning. But the FPGA is below this. Okay, FPGA is below this. So that data will go to the FPGA, and that is a digital data. So let us assume this is 1 volt. Okay, 1 volt is the input to my ADC. ADC will generate a digital output. Okay, the ADC output could be serial. That it could go 1 0 1 1 1 0 0 0. It could go, and it will go into the FPGA. If this is the case, only one pin of the FPGA is used. But it could also be like this. I have 1 volt. I go to the ADC. Okay, and ADC can generate multiple. Okay, and that could go to the FPGA. That could be 1 0 0 1, etc. Like that. It could be a serial ADC or it could be a parallel ADC. So which ADC, those requirements, all that will be taught in the future, in the later part of this course. But just for information that the FPGA can only interact with digital signals. So it cannot interact with an analog signal. So to feed the real world signal to the FPGA, it has to be processed by an ADC to convert it into digital data, which will then be used by the FPGA for its operation. Okay.
Sir, in this board,
yes,
we are having a bypass. Sorry, a wire for measuring the current.
Yes. This one.
The red one.
Yes.
Sir, so is there no connection on the boards? Board also will have some connection.
This is connected to the board. See, the current will flow like this. It will flow like this. Okay.
So on the board there is no trace. Is it, sir?
Yeah, over here there's no trace. Instead, it's this node or this part is not connected to this node. Okay, so for connecting that, we have this wire to close the path. So this way we are measuring, this is the inductor, and this way we are measuring the current flowing through the inductor because it is in series with the inductor. These various current sensing techniques will be shown in the later part of this course. Okay. So I'll proceed. Okay.
Yes.
So this is the Nucleus U474RE microcontroller, and this is the TI microcontroller, C2000 series. So this is another board which can be used. And this is, so TI microcontroller and STM microcontrollers, they are very popular options which are for microcontrollers. And if you want to learn microcontrollers, these are very good things. The industry experts have demonstrated in one of the weeks, I think week 8 or 7, about these microcontrollers, the overview and how to use them, etc. So you can refer to that, but they'll what they've taught is limited, and if you want to actually use them, you have to go more in depth and check out, right? Now we will proceed to actual how will we control a DC-DC converter. So this is the schema, like this is the circuit of a buck converter. If you will observe, this is the switch. This is the main switch, active switch. This is a complementary switch. So if this is 1, this is high, and this will be off. And if this is 0, this will be 1 and this will be on. So at an instant, both cannot be on. Both should not be on. Okay. This is the parasitic resistance. There is not physically a resistance is not connected, but to model the on resistance of the MOSFET, it is shown by this resistance R. Similarly, this resistance R2 models the parasitic on resistance of this switch S2. So this is the inductor, and this is a sense resistor RS. So the voltage across this sense resistor is proportional to the current flowing through it, and that is sensed by a current sense amplifier. And that signal, that sense current signal, goes to this processing circuit. Okay? That is something later. So there's an inductor, and this is the DCR, the resistance of the inductor. The inductor also has certain parasitic resistance. Then there's a capacitor is over here, but it has some equivalent series resistance, ESR, resistance. So these parasitics are also shown in this circuit. Okay. Then this is R stands for the load resistance, and R1 and R2 is the feedback resistive divider. So this output voltage, suppose it is 3.3 volt. Okay. Now I cannot send 3.3 volt to my ADC. Okay, it has to be stepped down further. It will step down, say, to 1 volt, and then I can send it to my ADC. So all these are designed for the aspect, just a basic overview. So the signals, the output voltage, the inductor current, these signals are sent to the signal processor and the signal conditioning part of the board. Why are we sensing these signals? We are sensing the inductor current and output voltage because we want to control the DC-DC converter to operate as per our requirements for our particular application. So we need these signals to control it. Output voltage and inductor current. And those signals are converted and stepped down and processed such that it can be fed to our controller. Okay, and the controller will implement some feedback or feed-forward control techniques, and it will generate some gate signals, and those are some values or some reference values, which is translated via modulation techniques to generate the gate signal Q. So from here, output voltage inductor current sensing, it is translated into some effective gate signal, which turns on and off these switches such that the buck converter performs our specific requirement. All right. Now we will proceed further. So first we will start the feedback or feed-forward control methods. what are those? So what are those methods are there? Feedback and feedforward. And there's a paper, a tutorial review discussion, which is an open journal thing, which is accessible to anyone who doesn't even have IEEE membership. They can read it, where a very comprehensive set of written theories written about various control techniques or modulation techniques, etc. Now, why do I need feedback or feedforward? I want the output voltage to be regulated. I want the output voltage of a buck converter to give me 1 volt, irrespective of the, whatever is the load, whatever is the input voltage applied. So for that, I need to regulate the output voltage. Also, I want load transient performance to be good. Okay, it's like if the load is increasing like this is my output, load output current. What will happen is the voltage will dip. Okay, it will dip and it will come back. So this dip should be limited. It cannot dip indefinitely and then come. I don't want it to be like this. So this is a better transient performance. So it should meet the control using feedback and feedforward. I need to be able to achieve the desired transient performance.
Sir, when there is a sudden change in load, why it is a dip? Could you please, sir?
Yes. See, the capacitor current is equal to the inductor current minus the output current of the buck converter, for a buck converter. Okay. So in normal operation, the average value of the capacitor current is 0, because we are regulating the voltage of the capacitor. But what happens when there is sudden change? Suppose
Sir, average current through inductor capacitor, you are saying 0. Okay.
Yes. Through capacitor, average current is 0. So when the output current suddenly changes, in that case, the capacitor current, average capacitor current is not 0. See, what do you mean by average capacitor current? It will be like this and like this. This is 0%. So this is the average capacitor current. But suppose, please don't write anything here. So suppose there is I output goes from 0 to 5. Assume. What will happen? The capacitor current will then be like this. So when it is like this, what it is more, it's gone in the negative region. Average value of the capacitor current is negative. When it goes into this region, what will happen? The capacitor will start discharging. Okay. When it starts discharging, what will happen? The output voltage will reduce. It will dip. If it was like this, it will dip like this. Okay. Then what will happen is because it is dipping, the control, the feedback and feed forward, it will change. It will change this. It will modulate and change this Q in such a way that this dip, when it has fallen, it will come back to its original voltage, original set point. So that is the use of control. Okay. So it is there for regulating the output voltage. Now, what will happen? So what we know is this could change. The load current could change. Another thing could happen is this input voltage could change. If this input voltage changes, what will happen? The output voltage also would change. If this input voltage increases, output voltage also would increase, but that is not what we want. So then our control should be able to reject these disturbances in the input voltage, disturbances in the load current, etc. Then see, the current to the inductor is like this. Okay, has a frequency. Okay, and because of these flowing and because of the various passives, various parasitics, etc., it results in electromagnetic interference signals are generated. Now, we do not want the certain requirements that this application should not generate this sort of an EMI which exceeds certain value. So we have to use a modulation and control technique to limit the EMI which would be generated. Another thing is the inductor current cannot just go to a very large value. It should be capped off. It should be stopped. And if it goes about some certain value, it should be stop. It should be turned off and it should again start falling. So all this can be done, implemented via control. Okay, this meeting will end in 1 minute. So I will again start a link and then you can again join this. Okay, till then I will continue. Then we want to achieve a flat efficiency curve over wide load current range. What happens is many times the efficiency curve is like this. Okay, after some point it starts dipping. Oh, wait.
Sir, how the EMI is reduced, sir?
How the EMI is reduced? There are certain advanced techniques which are there, but that is a very a high level topic actually. Like they have some frequency by frequency spread spectrum or hysteresis control. All these can help to decrease the EMI. All that. So I'm audible, right?
Yes, sir.
Yeah, so I proceed. So another thing is we want to have a flat efficiency curve or a wide load current range. So if the load current changes, there could be a place where the efficiency is high, then it could reduce. Could be here, it could reduce. We don't want it like this. We would prefer the curve to be approximately flat. Okay. This is the efficiency. This is the load current. We prefer it to be a flat. Even though the load current changes, the efficiency should be quite high. But it could be like this. The curve could also be like this, and this is not desired. So we prefer it to have flat efficiency curve or a wide or a low current range. Okay. Another thing is stability. That our control, which we implement, it should be stable. It result in stable operation. Large scale stability as well as small scale stability. Now we will go to the basic single feedback loop voltage mode control. So this is the logic. There is a DC-DC converter. It generates an output voltage that is sensed by some resistor divider or some sensing techniques, and it is scaled down to VFP. It's compared to the reference value, and that will generate an error signal. That error signal passes through a controller, and this will generate a control signal. That control signal will be compared with this RAM, which is generated, and that will generate pass to the PWM block, and it will generate the gates. Let us see how it happens. This VCon, let us ignore this and let us see VCon is a straight line.
How GC converts the error to VCon?
That is the controller, no? PID, proposed internal controller. They convert it. Okay.
Sir, where can I get that information to know, sir?
Actually, there's the previous NPTEL course, Control and Tuning Methods for Switch Mode Power Converters, again taught by Professor Dr. Santava Kaput. So there he has explained in depth these things.
Okay.
Yeah. There you can learn. So this error voltage gets converted into control value, control signal. If there are certain fluctuations, okay, let us consider no fluctuation. Let us assume this is my RAM signal. So it's coming like this. Okay, this is this VR signal. And this is my control. value. So whenever VR is, whenever this VR, this is VR, the ramp is VR. Whenever VR is greater than vcon, what will happen? This will be 1. Okay. And that will be 1. Okay, plus this PWM block. So what exactly we want is, when this is 1, this is QC. Okay, QC. If QC becomes 1, it will reset. Do you know what is a SR latch? Okay, this is a SR latch. What happens in this SR latch is, we will give a set signal at particular time interval. So it is high. You give a set signal and it is high. Then what happens when this vcon, when VR crosses vcon, this reset will become 1. And when reset becomes 1, this will become 0. Okay, this will become 0. And like this. Again, when this becomes 0, we give the set signal. It will go high. And when it crosses this point, it will again go low. So this is Q. Okay.
Sir, can I change the V control in place of VR and VCon in place of VR? And that is comparator output is given to S and the FSW is given at R. Can I do that like that?
Yeah, you can do that. That will become a different modulation technique.
Okay. I want the same. Sir, can't I implement the same trailing edge PWM by interchanging VR and V control and the FSW with QC? Can't I get that, sir?
No, you cannot. Then it will become leading edge PWM. Not be trailing, it will be leading edge. But it will, but your converter will work. If you invert the logic, the converter will work. It's not that it won't work. It is just a different modulation technique. That's all.
Okay. What's the difference, like trailing edge and leading edge? The edges are changing with respect to the reference and control voltages. Other than that, is there any difference, sir?
No, there's, see, this is, there are some research papers which say some certain differences and usefulness of these techniques. But those are like very high advanced topics. It will work. Your converter will work, but this is the standard way in which they do. Okay. It's not that if you go from trailing edge to leading edge, my converter will not work. Might work. But there might be some practical reasons also why they prefer it. See, all this which we are seeing, it is just a logic level we are seeing. But when you go to a practical circuit and you try to implement it, there might be reasons why trailing edges prefer to leading edge. Okay, there could be some practical reasons which right now is just too much for you to handle. So that is why they prefer trailing edge. Okay, that's the reason. So yes, yeah.
So actually, the one we are using for the SR latch here, this is the leading edge PWM, right?
No, this is trailing edge.
Okay.
Why it is trailing edge?
Sir, how is in?
Yes, actually, why it is trailing
edge? We are comparing with the VCon and VR, no? VR to get a Q signal.
Yeah. Yes.
Sir, when VR is greater than VCon, then only we have to get 1, no? Generally.
Yeah. Yes. So
then,
this tell.
Signal Q is something different, I think. When VR is greater than VCon, then only we'll get 1, right?
No. See, SR flip-flop is, if this is set, reset is also there, it will show the previous state. Okay. This is 1, this is 0, it becomes 1. Like that it is. Only when it is a tell.
Sir, the trailing or leading is dependent on just on the comparator itself or on the R?
Or on the R. You see, it is trailing edge or leading edge based what is happening over here. At this particular crossing, this is falling. That's why it is not trailing edge. Okay, at this particular control
The pointer is
event.
not visible.
Okay, now is it visible?
Yes.
At this particular event, what is happening? My gate signal is going low. It is falling. This is my control event. And at that time, the signal is falling low. That is why it is known as trailing edge modulation. Okay. If the logic was in such a manner that at the particular control comparison event, the gate signal was going high, then it is known as leading edge modulation. Okay, we will look into that in the later slides. So, any doubts? Or I'll proceed further.
Yes, sir. Yes, sir. We can proceed.
Now we will go to current mode. So voltage mode control has some sort of limitations and designing and all that. Current mode control is quite popular. And current mode control consists of two loops. There's an inner loop and there's an outer loop. So the output voltage, outer loop is slower. It has a lower bandwidth, and the inner loop is faster. Okay. What happens is the output voltage gets compared to the reference. It generates a error, V error, that passes through this controller, and it generates an icon. This icon is compared with the sensed value of the inductor current, and further use reset and set pulse. Similar thing. We will look into the operation here. We will look into this operation further. Okay. Basically, there are two controls. We are controlling the inductor current via icon and the output voltage via Vref. Okay, and they are linked. They are interlinked. It is a two-loop control, cascaded control, where the inner loop is faster, much faster than the outer loop. Outer loop is slow, the inner loop is faster.
Sir, can I interchange the V naught and IL like in inner loop and outer loop?
No, you cannot actually. Because the inductor is like this is the ripple of the inductor, no? It is lots, while the output voltage ripple is very less. That's why the bandwidth of the outer loop is slow, while the requirement for this bandwidth is slow, while the requirement for this is high. That is why we have the inner loop to be inductor current and outer loop to be output voltage.
Sir, bandwidth in the sense how the bandwidth for IL is high?
The bandwidth of IL is high because we have certain specifically. No? We design the outer loop slower, much slower than the switching frequency. So that way the outer loop is slow, but the inner loop is fast because it has all this ripple information.
Sir, and one more thing is like in the before, like when the error is given, the output is V control. But now here I control. How that G gives I here, there it gives V control.
See, this icon, those are just variables. They are not anything. You can write something as X, you can write something as Y in algebra. Doesn't mean anything. Okay. Physically, they are just in the physical circuit, the actual practical circuit, they are just voltages. That's why this inductor current gets converted into an equivalent sensed voltage with some particular ratio. All these stuff we will learn in the further weeks, later weeks. All right. Now, yeah. There is another concept known as input voltage feed forward. If in this modulator again, in this ramp signal, okay, this ramp signal VR, which we have, if we incorporate the input voltage information into it, then it would result in a control where the voltage is independent of the input voltage. When there are changes in input voltage, the output voltage will be regulated. Okay. So what happens is, we know the V output is equal to D into Vn for a buck converter duty ratio. Okay. And that this D comes from this comparison. That is effectively V con upon Vu into Vn. So this becomes V con, Vu becomes KFF into Vn into Vn. So this and this get cancelled, so it becomes V con by KFF. So using this method, what is happening is the output voltage is becoming independent of changes in input voltage. So this is known as input voltage feed forward. Okay, it is not in this situation. Like if you see in the previous case, the output voltage is fed back and then passes to a controller. But here we are feed forwarding this input voltage. So it results in, the disturbances or changes in input voltage does not affect my output. Okay. Now,
can you please explain once again?
Okay. So the output voltage of a buck converter is D into Vn. Okay, and this D comes by this D, the effective duty ratio is actually equal to the V con value upon the maximum value of this. Okay, the maximum value of this. That is how the effective duty ratio is calculated. In this case, I am giving a ramp signal of maximum value 1 and I'm multiplying it by KFF into Vn. So the maximum value of this signal, Vu max, okay, Vu max will be equal to V con from KFF into Vn. So this is my duty ratio. Then that I will multiply by Vn, then this Vn gets cancelled. So by incorporating this method, I am generating an output. I am designing my buck converter to work in a manner where it is insensitive to changes in the input voltage. That is, the output voltage is virtually made insensitive to changes in the input voltage. Okay.
Sir, how the feed forward and feedback are different?
See, this one, it is not passing through a controller. Okay, the value is given. The raw value of the input voltage is translated into a signal where it is given for modulating the control. The control signal is being modulated by a raw value of the input voltage. Whereas in the previous case, the output voltage is fed back compared with the reference and passed through a controller to generate some reference value which modulates the control signal. That is why it is feedback. But in this case, the actual value of the input voltage is like processed and fed to modulate the control signal. So that's why it's feed forward.
Thank you, sir.
Sir, here, how we are arriving at this duty D equal to this V con by V.
Bu, okay. So you will see, okay. Let me draw. I have this ramp, okay? Ramp. Assume this ramp is there. Maximum value of this is 5. And this value of the V con is 2. This is V con. So effectively, my switch will be on for 250. That is, if 5 means it is 100, like this is 5. Okay. Value of this is 5. Value of this is 2. So my duty ratio is what? On upon the total time. That comes out to be 2 by 5. Okay. Because this determines how long it is on. This determines how long it is on. If this was if this week on was at 5, it would be on the whole time. But because it is at 2, it is on only for 40% of the duration. So my duty ratio will be equal to 0.4. Okay.
So that VU is the peak of the RAM.
That's why I wrote VU max over here. Here actually it was wrong. It should be VU max. Sorry. Okay. Yeah, it is the peak of the effective ramp. This ramp is there, it is multiplied by this KFF into VN. So this generates a ramp whose maximum value.
Sir, what happens if I didn't multiply it and just added it?
It will not work. Because it will generate some sort of offset and certain other aspects. See, using this algebraic analysis, we have shown that it is eliminating V input from changes in the duty ratio. But if you just add it, it might not eliminate it. That's all. Okay. If you can analytically prove that it is able to do that, then you can try it and you can come with a new control technique and you can get some patents and everything. But there are various ways you can check. See how this logic has come up is because someone has derived it and seen it could work. See, this also is not foolproof. There will be certain limitations of this. There will be certain constraints in which this will act. Okay. But for some particular range of operation, it will work. So in that range, we use this. Any other doubt? I'll proceed.
Sir,
further.
that.
Okay, tell.
So programming that microcontroller STM board and that Texas board. Which kind of software we need to learn for that?
See, ST microcontroller boards, they have some CubeMX software to configure the microcontroller, and then they use some IR embedded workbench to write the code, etc. TI uses some Code Studio or something, and other stuff. So those softwares are available on the website if you check. Those are freeware softwares.
But here in this course, we will be discussing only about the FPGA programming.
Yes, only FPGA programming. Microcontrollers are discussed. There is a week in which the industry experts are showing how they're using the microcontroller to run the STM32, how they're using it to run an actual hardware setup, somehow configuration steps, certain steps are there. And TI also they have told the various functionalities and possibilities, which capabilities of the TI 6000 microcontroller and some comparisons, etc. are provided. But the codes and actual implementation for understanding each and every step has not been provided.
Hello, sir. Are you going to continue this session after 8 o'clock also?
I don't know. Actually, I'll continue for a little bit further after 8 also because I haven't finished much. So, okay. So I'll proceed to load current feed forward. Now, we have done input voltage feed forward. Okay, why we do input voltage feed forward? In voltage mode control, changes in input voltage cause changes in output voltage. And for it to be compensated by the feedback loop, it takes time. Okay, so if we directly feed forward that input voltage information, we can regulate the output voltage faster. Okay, when there are changes in input voltage. That is the advantage of feed forward control. And this is used in voltage mode control because voltage mode control is susceptible to changes in the input voltage. For current mode control, what happens is changes in the output load current, I output, will cause a dip in the output voltage, changes in the output voltage. It is susceptible to that. It is good. It can handle variations in input voltage, but variations in output voltage, the performance is a bit inferior. Variations in output load current causes, it has an inferior performance. So to overcome that, we use load current feed forward. Okay, the actual information of load current is passed on and that enables us to get a logic which works faster. Okay, so the outer loop is same, just in the inner loop we add the load current information to generate a particular reference which would work faster. Okay, any doubts in this?
Sir, could you please repeat it once?
For voltage mode control, variations in input voltage have a effect or a considerable effect on the output voltage, and that's why we used input voltage feed forward for voltage mode control. In current mode control, variations of input voltage do not have much of an effect on output voltage, but variations in load current have a significant effect on the output voltage. Okay, the performance is poor, the load transient performance is poor. To overcome that, we can use load current feed forward. That is, we are actually feeding the information of the output current to the controller, okay, to the control implementation. When we do that, changes in output current will, which usually would cause a large dip in the output voltage, would result in a lower or smaller dip in the output voltage, or sometimes even negligible or no change in the output voltage, because we are directly feeding the output current information. Okay, these are demonstrated for the parts, like simulations, etc. So you can understand this topic in depth. So right now I'm just giving a basic overview, and this is not comprehensive and this is not complete, but just to kickstart your understanding. All right. Now we have studied various control techniques which are there. Yes. Someone saying something?
Feed forward. Sir, you are saying this feed forward technique provides a faster control than feedback.
Yeah. No. See, what actually happens is the feedback control, the loop is made slower. It is wantonly designed to be slower, otherwise there are certain problems. So because it has been designed to be slower, whenever there's a change in the load current, it takes time to react. Okay? It takes some time to react. It will react, but it will take time. Now to increase the speed by which it reacts, if we directly feed the information of how much change is happening in the output current, then it would react faster. That is why we use feed forward.
Sir, could you
Sir,
please
sir.
repeat the load feed forward control, current control once more? I am missing a bit.
Okay. So there is an outer voltage loop that is wantedly designed to be slower. Okay, it is a practical requirement. Because it is designed to be slower, whenever there's a change in the load current, it takes time for it to react. And because it is taking time, instead, if we directly feed the load current information as well, it would react faster. That is why we use load current feed forward. Okay. Any doubts?
That output current seems to be feedback
No,
in
it
the
is.
circuit.
See, feedback means it is passing through a controller. If it is feedback, see the output voltage, it is fed back and passing to a controller. But here it is not being passing to a controller. It is just directly generating a signal. It's not getting converted and processed by a controller. The information is directly given. While as in feedback, the information is processed by a controller. Okay, that is why it is feedback. So next, so now we did the thing for various control techniques. Now we will observe modulation techniques. This has to be translated into some gate signals. That is from modulation techniques. There's fixed frequency modulation in which the pulse of the width pulse is only changed. Phase shift modulation is used for some advanced converters, phase shift voltage, LLC. They require phase shift modulation. Pulse skipping is for light load conditions. Variable frequency modulation, there's constant on time, constant off time, or hysteresis control. So let us see trailing edge PWM voltage mode control. I have a comparator, VREF, VR and VCon. VR is the RAM. So this is my VR is changing like this, and this is my VCon is changing like this, and this is my set pulse. FSW is my set pulse. So I give the set pulse over here, and my Q will be on. Okay, I give the set pulse over here, Q will turn on. Because S is 1, it turns on. And it will continue to turn on even when S becomes 0. Okay. Now, when VCon becomes greater than VR, then QC will go low. This is actually wrong. So what actually should happen is this should be QC bar. Okay, this is QC bar. When VR becomes greater than VCon, then QC will become 1. So this is QC bar. So QC is actually a complementary version of this. So when QC becomes 1, when this becomes 1, this is reset. And then Q will become back to 0, just turn to 0. Okay, so actually let me draw QC. So QC will actually be like this. This will be QC. This will be QC. Okay. So what happens is this is set, going to your set. Okay. This is going to your reset. So set comes, becomes 1. Set comes, Q will become 1. Okay, it goes high like this. Then, and at that time QC is 0. When QC becomes 1, R will become 1 and Q will go fall down to 0. So this is actually your trailing edge PWM voltage grid control. Okay. Now, because there is noise, certain noise can be there. In a practical circuit, there will be noise, and we want it to not affect our implementation. So we use this SR latch. So anytime there are, there are these sort of jitter, sort of noisy things, noisy transitions, this undesirable. What happens at the first time R becomes 1, it will go drop to 0. The very first time. If it becomes 1, then it goes to 0, again becomes 1, again goes to 0. This will be off only. It will not change. We do not want it to change. Okay. We do not want it to again turn on. We want it to be off, means it is off. Once the signal comes, like you switch it off, it is switched off. Then even though there is a certain transition, it says we turn it on, it will not turn on. That is why we use this SR flip-flop, SR latch for implementation. Okay. Now we will go to peak current mode control. In peak current mode control, what happens is this is my signal, okay, inductor current, and this is my reference value, icon. So when what will happen is the inductor current will rise and it tries to go above this icon. When it tries to go above icon, this will become 1, and then this will turn it off. Okay, it will turn it off. What happens at the start? You get a set pulse. You get a set pulse. So that time Q will become high. Okay, Q will become high, and the inductor current will start rising. The inductor current starts rising. When it tries to go above this one, then QC will become 1. That means reset will become 1. That will mean Q will have to fall. So Q will become 0. Okay, so this is the way peak current mode control is implemented. In this manner, the peak value of the inductor current is limited to this value. Okay, it will not rise above this. That is how we control the inductor current.
Sir, how this trailing edge and peak current mode control are same? Could you please say that?
See, peak current mode control is just a technique. It is called trailing edge. Why? Because the control transition is happening over here, where actually the gate signal is falling. And because the gate signal is falling, that is why it is known as trailing edge. That is the only reason it is known as trailing edge. So as peak current mode control is there, we can also have valley current mode control. In valley current mode control also, what is there? This is the valley. So here, like the reset is given by this. Okay, we give these pulses. We give fixed these pulses which are of fixed duration are given to the reset. So we get a reset pulse. The inductor, so the Q becomes 0 in that case, and the inductor again starts falling. It starts falling. Okay. Then when it reaches the valley, and because it reaches the valley, we do not want it to fall further. We are controlling the value of the inductor current. We do not want it to fall further. So when it reaches this value, QC will become 1 at that instant, set will become 1, and Q will turn to 1. Okay, so Q will become 1. So this is the period for which it is off, this is the period for which it is on, and this is the fixed time period. Okay. Now we'll proceed to constant on-time modulation. So these are examples of fixed frequency modulation. But let us go to constant on-time modulation, where so we have a reference voltage over here and we have an output voltage over here. Okay, whenever the output voltage falls below the reference voltage, it gives a trigger. Okay. Whenever output voltage falls below the reference voltage, this QC will go high. When QC goes high, it generates a rising edge trigger. Okay, rising edge. That will generate a trigger signal which will go to a monoshot timer, and that will cause this pulse to be on, okay, for a fixed duration. Any doubts on this?
So again, when V0 goes higher than V reference, then at that time QC will become 0.
Yeah. So see, this is an edge triggered circuit. It's not a level trigger. Means this F trigger will be 1 only when QC rises. When it rises, it will be 1, and after, when it is stable, it will go back to being 0. Okay, so you would see QC is 1 over here. QC we draw is 1 over here. This is the way QC is. This is the signal of QC, but F trigger is just a short duration. When QC rises, that time F trigger will become small. So it is an edge trigger thing. It is not a level trigger. It is not when QC is 1, F trigger is 1. It is when QC is rising, that transition, when it senses that QC is rising, then F trigger becomes 1 for a short duration, and that will cause the monoshot timer to be high for a fixed duration, but for which it has been programmed for.
So after the moment at which it sees the rise, the Q will be on for some time.
The QC goes high. At the instant of QC going high, F trigger goes high. F trigger goes high. At that instant, the monoshot timer gets triggered, and it will remain on for a fixed duration depending on what you have programmed into it. So once the F trigger signal comes, sorry, let me just. So once the F trigger signal comes, the Q will be on for a fixed duration. Okay. So this is constant on-time modulation. So anyone has any doubts in this? Okay, by the way, let me stop sharing. You guys have started watching this course. Have you seen the previous NPTEL course, Control and Tuning Methods? Like anyone of you has checked it out before?
Yes, sir, we have checked, but we are unable to cover all those. I covered a few of them.
Okay.
Sir, is it need to cover all the lectures to understand?
No, there's no need. No, wait 1 minute. First, this meeting will end in 1 minute, then we will again join. Okay. So, see, you need to, if you are able to understand why we are doing constant on time, why we are doing peak curve mode control, valley curve mode control, etc., then there's not too much of need to know that, because sir will give the overview. But in case of finding it that you're not able to understand still, then it would be required for you to go through those lectures. Okay. So I'll proceed with constant off-time control. So constant off-time control is opposite to constant on-time control. And it is like similar to peak current control. The peak is the situation at which it is getting triggered. Okay. So when the inductor current reaches the peak value, it gets triggered, and then there's a off time, fixed off time for which it is off. See, what happens is, let me put my pointer. It is, the off time is fixed. This on time can change depending on the icon, but the off time is fixed in this implementation. That is why it is known as constant off time control. And because the off time is fixed, but the on time can change, then what will happen? The effective time period changes. That is why it is known as a variable frequency control. All right. Any questions in this? So there is also voltage-based implementation of constant off-time control. Okay, and there's current hysteresis control. So this is a very this is also a technique which is used a lot. So in hysteresis, what we do is we are maintaining the inductor current to be within the particular band. Okay, there's a maximum value of the current, and there's a minimum value of the current. So what happens is the switch turns on, the current rises. When it reaches the maximum value, it turns off. When it reaches the minimum value, it turns on. So it turns on and it rises. It reaches the maximum value, it is switched off. Then the current falls. So this is the current hysteresis control, which is implemented by this logic, okay, by this RS batch, and by these two comparators. So using these comparators, we implement current hysteresis control. So if you want further details of it, you can refer to lecture 22 of the previous NPTEL course. Now we start with buck converter voltage mode control. We'll start with the basic voltage mode control, where the output voltage is sensed. It's compared with the reference voltage. Error is generated, goes to the controller. This generates the comparison value, which is compared with the RAM, and that actuates this RS flip-flop accordingly to generate a gate signal Q. Okay, so this is the analog implementation of this. In the analog implementation, as I said, there are these RC filters. Filters are used to implement a type 3 compensator. Okay, this feedback signal comes over here, and this is the error control signal which comes over here. Okay, and the error is etc. All of that is happening internally. V feedback comes over here, reference is over here, and it is generated VC, which is comes generated as VC from the output of the op-amp. All right. So this is analog control, but now I want to go to digital control. So what I will do then? I will change this VREF. VREF, I will make it digital. I will program it that I can program VREF accordingly. So I will have a DAC. Okay, there will be a DAC. There will be a DAC, right? We'll give VREF digital. That will be converted into this VREF analog. So the whole entire loop is analog. VREF also is analog. But this VREF, analog VREF, can be programmed via a DAC. A DAC stands for digital to analog converter. So that value which I want, that can be programmed. And that goes to a DAC, and that will give me my VREF. So this is known as a housekeeping arrangement for voltage node control. Then I could do even further. VREF, I can leave it to be already in digital domain. I can use an ADC over here. The ADC will convert output voltage into a digital value. That will be compared with VREF, which is a digital value. It will generate an error signal, which also is digital. Then what happened? This also has to be converted to digital. When this gets converted to digital, this also will get converted to digital. Then it has to be compared with a digital value on it. So this ramp also will become digital. And a digital ramp is implemented by a staircase. Okay. Analog ramp is just a straight line, but a digital ramp is implemented as a staircase. Okay. So any doubts in this?
Sir, how that ADC, why you used that ADC there?
The ADC is used to convert the analog signal into a digital signal. Okay. In this case, this DAC will not operate. So VREF is digital. Process we converted digital values. So I pass to ADC. It will be shown in the next slide. Okay. This is how it is. I have output voltage. The output is in analog domain. It gets converted into a digital value. Then it is compared with VREF. This also is in digital. Then it goes to VE. That will generate an error voltage also is for the digital. That goes to this digital controller. And this is compared with a digital ramp. Okay, digital ramp. And that will generate my reset pulse, and reset pulse is given accordingly. And with a suitable dead time, I will generate these pulses for this clock converter.
Sir, actually, I think the output voltage is not digital, it is analog, right?
Yeah, this is analog. It is converted to digital via this ADC. Can you see my pointer? This is the ADC. This is analog. This is digital.
Okay, sir. Okay.
Okay. So accordingly, it will implement the logic. Now we will go to analog current control. So this is how current control is there. Two loop control, inner loop and outer loop. Now, if we digitize, what do? Is we convert the output voltage into digital domain. So the output voltage, the feedback voltage is converted by an ADC into a digital value, which is compared to the digital reference input. Okay. It is converted into digital value. and then it is compared, and then the digital controller generates a beacon, which is converted into an analog signal via a DAC. This analog value is compared with the sensed inductor current, which is in the analog domain, and that will generate the reset and set pulse to accordingly actuate, control the DC-DC converter. Okay, so this is a mixed signal current control, where the inner loop is analog, where the outer loop is digital. The digital value of the output voltage is converted by ADC. The analog value is converted by ADC to a digital value. That goes to the controller, which generates a reference value, VCON, which has to be converted into analog domain via DAC, so that that can be used for comparing with the sensed inductor current, and that will modulate this DC-DC current. Okay, so this is known as mixed signal current control. So the current loop is in analog and voltage loop is in digital. Then there could be a case where both are in digital, where the output voltage also is being converted by ADC into digital format. The inductor current also is converted by ADC into digital format. And this entire implementation is happening inside the digital platform, inside the FPGA. Okay, we are using FPGA. But what will be the difference in this case is this sampling rate of the output voltage would be less than the sampling rate of the inductor current. That is, the inductor current samples should be taken at a much higher rate than the output voltage samples. As I told, because of the bandwidth requirements. Because we need the ripple information of the inductor current to perform current mode control. Okay. So the digital current with high current loop sampling rate. So current and voltage feedback both are in digital domain. Next, let us consider current mode control architecture 3, where I'm sampling output voltage and I'm sampling the inductor current as a value. But inductor current sampling doesn't require to be very fast. Instead, I'm using a ramp. Okay, an external ramp I'm using, and this is providing a sort of ripple current information, and these output voltage and inductor current can have the same sampling. So this is another type of digitization of current mode control architecture 3. Okay, this is with ripple emulation. This performs the ripple emulation. Okay, so these are further things for ripple output voltage, further things which you can ignore as such, which like we cannot discuss now because the time is past. These are also some questions which I thought you guys could do. So I will be uploading these questions, this PPT and these slides PDF, so you can solve these questions on your own. If you have any doubts, you can ask in the next session. Okay. So any last queries or anything?
Sir, I have a great inertia. Why and how we are moving from analog control to digital control? There is a great inertia for me to understand and diagram. Is there any simple understanding for my question?
No, like you want to know why are we going from analog to digital?
Yes, sir.
No, see, in analog, as there are lots of limitations in analog, and it is very, you probably have not made a actual implementation in C. Like, you have to have a RC. Okay, these RC over here. These to find them, to solder them, to check them, then if you want to be a very hard. And for some simple logic you can implement it in analog, but for complex and comparison and event based logic, you need to go for digital. Okay. See, this course is a very difficult course, I agree. It will take lots of effort to learn it, but it is very practically useful.